In this video, we're going to get an introduction to trigonometry and some basic trigonometric functions. Believe it or not, I remember being young like you and being a little intimidated by that word trigonometry. But actually, it's not too complicated. It's very useful, and it applies to any right triangle, so we don't have to have any kind of special setup. So actually, it might be one of the easiest things we do in this unit. We just have to get a visual of what's going on. So let's take a look at this. The word trigonometry, it sounds scary because it has so many syllables, but really the two parts of that word, the first half applies to triangles, and the second half just talks about the measure. And so trigonometry is really just looking at measurements in triangles, whether we're looking at the sides or the angles. And what trig does for us is it puts a relationship between our sides and angles. And so if we have just a little bit of information, we'll be able to know all the angles in the triangle and all of the sides in the triangle as well. Okay, so there's lots of trig functions. Some of them get a little complex for some big things, but we're just going to keep it pretty basic here and just look at the main three, I would call them. They come up so often, and they are known as sine, cosine, and tangent. And you see that we just use three-letter abbreviations for these. So for sine, we just use the first three letters, and cosine and tangent. We just use the first three letters of each of those to represent them. So how this works is, in this diagram here, if you want to talk about the sine of an angle, and a very common variable to use for angles is the lower Greek letter theta, and it looks like a circle with a slash through it. That is a Greek letter. It gets used for angle measurements very frequently. And so if we want to talk about what's called the sine of this angle here, we would use a ratio of the side that is opposite to that angle, so the side that doesn't touch that angle, and the hypotenuse. And that relationship is shown with, we put sine of theta equals the opposite side over the hypotenuse. So we set up a fraction over here, a ratio of those two sides. Very similarly, with this same angle theta, we could talk about what's called the cosine of that angle. And the cosine is found by using the adjacent side and comparing it to the hypotenuse. And so in this scenario, we say that the cosine of theta is equal to the adjacent side over the hypotenuse. We set up this fraction. Hopefully remember that word adjacent means next to. And so it'd be the leg that is next to theta over our hypotenuse. And lastly, we have the tangent of an angle, which does not use the hypotenuse. It uses the opposite side and the adjacent side. And so here we can say that the tangent of this angle theta equals your opposite leg over your adjacent leg. Okay, and so we have three different trig functions that we'll use, which use three different pieces of information. Sine, all you need to know is the opposite and the hypotenuse. For cosine, you only need to know the adjacent and hypotenuse. And for tangent, you only need to know these two sides, the two legs. And so no matter what setup you have, as long as you have two side lengths, we can start talking about one of these three functions. Now, very commonly, we use a mnemonic device here to talk about sine, cosine, and tangent. We say so, ka, toa. So being the three letters S, O, and H, because S stands for sine, O stands for opposite side or the opposite leg, and H stands for the hypotenuse, because sine is equal to the opposite over the hypotenuse. Same thing here. Ka, C-A-H, would be cosine equals adjacent leg over the hypotenuse, and toa would be tangent equals opposite leg over the adjacent leg. Okay, I know still sounds a little confusing. Let me show you how this can work for us. So I've got several examples here on finding an unknown side length. So you can see in each of these diagrams, we have an angle measurement given, we have a side length given, and we're going to find another side length. Now we have three different trig functions, and so as long as you have two pieces of information, you should be able to apply one of the three. And so we'll look at two cases where sine can help us, two cases where cosine applies, and then two cases where tangent will apply as well. So let's get a look at this. For sine, we have this 20-degree angle here. And you notice that we have this W that's all the way across from 20. So this side does not touch the 20-degree angle. This is considered the opposite side because of that. And we have this side across from the 90 degrees, which we have always called the hypotenuse. And because we have the opposite leg and the hypotenuse that we're interested in, that is why we use sine, right? So we simply write this as sine of 20 degrees equals your opposite side of W over the hypotenuse of 24. Okay? Very simple there. That's the setup. We'll solve it in just a moment. Let's go ahead and set up the next one as well underneath it. You notice again, we have this angle 35. We're given the side across from it, the side opposite from it, the leg opposite of 35, which we call, which is 6 centimeters. So here's our opposite side. And B is across from 90 degrees, which we have always called the hypotenuse. And so once again, because we're referring to the opposite leg in the hypotenuse, this is the ratio for sine. So we say sine of 35 degrees equals opposite, which is 6, over hypotenuse, which is B. And so I chose these two because you notice one case is going to have our variable in the top of the fraction, and the other case has in the bottom. And we'll talk about how to address that. Okay, so there's the setup for both. Let's go ahead and set up the other two. Tangent over here, or cosine, sorry, would be these middle two cases, because you notice in this top example, we have a 32-degree angle right here. So here's an angle that we have. And the two sides that are marked, one of them is across from 90 degrees. That's always the hypotenuse. And the other is the leg that touches that angle. It's the leg next to that angle. And we call that the adjacent leg. Okay? And since we're referring to the adjacent leg in the hypotenuse, this is cosine of 32 degrees equals adjacent leg x over your hypotenuse 17. Okay, very similarly underneath here, another case where you have an angle given, 47 degrees in this case. You have the hypotenuse that has the variable q, and you're given the adjacent leg, the leg that touches the angle. And so because we're referring to the adjacent leg and the hypotenuse, that would be a ratio that describes your cosine. And so once again, we say the cosine of our angle 47 degrees equals adjacent leg of 12 over your hypotenuse q. Okay, let's set up this last case as well. So tangent, very similarly, we have an angle, in this case 37 degrees, and we have two sides marked. They're your two legs. And so x is the opposite leg from this angle because it is the leg that does not touch the angle. And this is the leg that does make the angle, and so we call this the adjacent leg. And so in this scenario, we say that tangent of 37 degrees equals your opposite leg of x over your adjacent leg of 12. Okay, and one last scenario here, another one. We have the angle 50 degrees, and if you haven't caught on, it doesn't matter how big the angle is. What we look at is what sides are provided related to this angle. And so if we have 50 degrees right here, you notice we have the two legs marked once again. 20 is the leg opposite from this angle, and y is the leg adjacent to this angle. And so what we can write is that tangent of 50 degrees equals your opposite leg, 20, over your adjacent leg, y. Okay, so there's the setup. It's like that every time. We just need to figure out what two sides are marked in relation to our angle. So we need to pay attention to whether we have the opposite leg or adjacent leg to determine sine and cosine. But once we get here, solving isn't too bad. It's really just some basic algebraic steps and using a calculator. So let's look at these top scenarios. If I want to solve up here for sine, notice over here I need to solve for w, and w is being divided by 24. And so all I need to do to solve for w here is multiply by 24, just like we always have. And so over here, the 24s will cancel each other. Okay, so if I'm going to multiply by 24 here, I need to multiply by 24 over here. Okay, and so what we get is that 24 times sine of 20 degrees equals w. And what is that? Well, sine is just a ratio of sides, but good news is calculators have been programmed to give us some decimal approximations for these angles with trig functions. And so if we go to something like the Desmos Scientific Calculator, and we type in what we had, which was 24 times sine of 20 degrees, and you don't have to put the degree symbol here. Automatically, we're set up in degree mode. Once you type that in, you get a decimal approximation. So 24 times sine of 20 degrees is 8.208, and so on. It keeps going forever, it seems like. And we're asked to round to the nearest tenth, which would be the first decimal place. And so this rounds to 8.2. And so for this, we get an approximation that w, that missing side that we were looking for, is roughly 8.2 units long. So through a trig function here, where we could find this missing side length when we didn't have any other option, because we couldn't use Pythagorean theorem, for example. We don't have two of the sides given. So trig is allowing us to find missing side lengths when we haven't been able to in the past. Okay, so let's stay on this trend here. Let's try out this top case here for cosine. Same deal. I need to solve for x. It's in the top of the fraction, so to cancel the 17 in the bottom, very simply, multiply by 17. And if you're going to multiply by 17 on the right, you should multiply by 17 on the left. And so we get 17 times the cosine of 32 degrees. Okay. And over here, those two values will cancel. So on this one, we'll put 17 times the cosine of 32 equals x. And once again, we just go to a calculator, type this expression in, 17 times cosine of 20, and get our decimal approximation. So 17 times cosine. And I just realized I think I put the wrong angle measure down. I did. The angle is not 20 here. That was the last example. The angle is 32. So let's fix that. So 17 times cosine of 32 degrees. Type that in, and there's our decimal approximation. We get 14.41, which rounds to 14.4. Okay, so let's put that down, and now we have an approximate value. That missing side of x is roughly 14.4 units long. Okay, let's try this one more time. So finding this missing side, x again. And we have tangent of 37 degrees equals x over 12. So same strategy, multiply by that denominator of 12 to cancel over here, which means we also have to multiply by that 12 on the left side. So we get 12 times tangent of 37 degrees. And let's write that out, and then we'll get our decimal approximation. So 12 times tangent of 37 degrees equals x. Let's go figure out what 12 times the tangent of 37 is. And it looks like we get 9.04, which would now round to 9.0 or just 9. So 9.0 equals x. Or we could just put x equals 9. Okay, so pretty basic, right? A simple multiplication, type it into a calculator, and we get that decimal approximation. So this side over here is approximately 9 units long. Not exactly, but it's very close. Okay, so what's different down here? It takes a little more work to solve when the variable's in the bottom of the fraction, but there is a very simple strategy here. When you have the variable in the denominator, an easy approach is rewrite these as proportions. Okay, put sine of 35 degrees over 1 equals 6 over b. Cosine 47 degrees over 1 equals 12 over q. Same here. Because now you can see that we can just cross multiply. We didn't have to write it like this, but maybe that helps us see what's going on. So if we cross multiply in this scenario, we're going to take b times the sine of 35 degrees. So let's show what we get there. We get b times the sine of 35 degrees equals 6 times 1. That's just 6. Okay. Same over here. Cross multiply, we're going to get q times cosine of 47 degrees equals 12 times 1, or just 12. And in that last scenario, we get y times tangent of 50 degrees equals 20 times 1 is just 20. Okay, go and put that multiplication symbol here. So to solve for our variable now, to solve for b, notice it says b times 35 degrees. We just need to divide by 35 degrees on each side. Put that in a different color here. So if we just divide by sine of 35, that's what we need to type into our calculator. So b equals 6 divided by the sine of 35 degrees. And all we need to do now is go to a calculator, get that decimal approximation. So 6 divided by sine of 35 degrees gives us a decimal approximation of 10.46, which will round to 10.5. Okay. All right, well, let's use that same strategy over here. To solve for q, we need to divide by cosine of 47 degrees. So we'll divide by cosine of 47 degrees here. And we're going to get q equals 12 over cosine of 47 degrees. And that decimal approximation, let's go type that in. 12 over cosine of 47 degrees gives us a decimal approximation of 17.59, which will round to 17.6. So that means the hypotenuse here is approximately 17.6 units long. Okay. And last scenario, with tangent of 50 degrees, we need to divide by that to get y by itself. So we divide by tangent of 50 degrees on the left side and again on the right side. And what happens? We get y equals 20 over tangent of 50 degrees. And again, let's go get that decimal approximation. 20 over tangent of 50. And there we go. We get 16.78, which is going to round to 16.8. So decimal approximation here, roughly 16.8. And so the adjacent side, this missing adjacent side, is about 16.8 units in length. Not exactly, but very, very close. Okay, so there's how trig can help us find missing side lengths. We just did some examples here to whether the variable was in the top of the fraction or the variable was in the bottom of the fraction. Okay, but in all these scenarios, we'll type into a calculator to get an approximation. All right, so if trig can help us find missing side lengths, then perhaps it can also help us find missing angle measurements. And the work is really no more complicated. Actually, I think it's a little more simple than it was before. So let's see how this works. If we find an unknown angle measure, we just need to know about inverse functions. So for every trig function you see, and we're going to keep it just the sine, cosine, and tangent here, there is an inverse function that undoes the effect of it. So in other words, there's a function that cancels with the trig function that you're using. So they're easy to identify because they use the same name as the trig function that you were applying. And so we see that in the table here. If you were using the trig function sine, the inverse of that is simply just sine inverse or arc sine. Okay. And so it uses the same letters as sine. We just use this little -1 as an exponent to show the inverse of it. Same here. Cosine of x has an inverse of arc cosine of x, where we just use that little -1 right there to show it's the inverse. And so these two things will cancel each other out, cosine and arc cosine. Tangent of x is the inverse of arctangent of x. And so these two functions simply cancel each other out. Let's see how that works. So in all of these examples down here, these last three, we're going to find a missing angle. Okay, so here we see we're going to find x, and this one it says we'll find the measure of angle t, and this one we'll find this angle theta. So we'll use sine, cosine, and tangent to do this. Let's see how that works. So this first setup, you notice that we're trying to find x, and we have two sides provided. One of those sides is the leg opposite of x, and the other side is your side across from the 90-degree angle, in other words, your hypotenuse. And so here, the reason we're using sine is that you have your opposite leg and your hypotenuse, and we write it as sine of x equals your opposite leg, 15, over your hypotenuse of 17. Okay, and here's what happens. We have x, and it's trapped in this sine function. And so what we can do is we can cancel this sine function with its inverse. And so if we rewrote this as sine inverse of sine of x, what happens is the inverse cancels with sine, and so those just go away, and you just get an x. How simple is that, right? I know it looks weird, but just like that, sine is gone, and we just get x. That's exactly what we wanted. And just like we've said in the past, whatever you do to one side of your equation, you should do to the other side of your equation. So we get sine inverse over here, or arc sine of 15 over 17. Okay, and so what we get is that x equals the arc sine of 15 over 17, and all we need to do is type that into a calculator. So arc sine of 15 over 17. You can either type that in with the -1 written like an exponent. It's not an exponent, but you could type it in that way. You could also go to your function button, and right there you see here's the three inverse functions we just talked about. Click on arc sine. I've forgotten what our numbers were, 15 and 17. Okay, so I type in 15 over 17, and we get a decimal approximation of 61.92, which rounds to 61.9. So in other words, x is approximately 61.9 degrees. So just like that, if you know two side lengths, you can find a missing angle measurement using a trig function. Very useful. So now we know that x is roughly 61.9 degrees. And if we wanted to, we could find the other angle as well, either using a different trig function or using the idea that 3 angles in a triangle have to add to 180. Okay, so let's try this again over here for cosine. We have, we're trying to find the measure of angle t. So what you can do here is put a variable. So you can put x, you can put y, you can put whatever you want in here. So here's a variable, I'll put y. And so we want to find this angle. And you notice the two sides you have, you're given the hypotenuse over here, the side across from 90 degrees. You're also given the leg adjacent to y. It's the leg that helps make angle y. And so that's why we classify it as the adjacent. And so the setup for this is going to be cosine because of the two sides that you have. And we simply write that cosine of y equals your adjacent 7.5 over your hypotenuse 9. And to solve for it, it's just like before. You use the inverse of cosine. We need to get y by itself. We need to get rid of cosine over here. And so if we use the inverse of cosine, what happens is this arc sine cancels with cosine. Arc cosine cancels with cosine, and you just get y, which is exactly what we wanted. So now we just have the letter y over here, and whatever we do to one side of the equation, we will do to the other. And so we have arc cosine of 7.5 over 9. And you might have noticed when I typed this into a calculator earlier, it put parentheses there, which is fine. Let me put that back in red since that's how it was before. Okay, and so we get that y equals our cosine of 7.5 over 9. Now, this is the exact value, but that doesn't really mean a lot to us. So that's why we go to the calculator to get this decimal approximation. Arc cosine of 7.5 over 9. Here we go. Function, arc cosine, 7.5 divided by 9. And you see that we get a decimal approximation of 33.55, which rounds up to 33.6. Okay, so y is roughly 33.6 degrees. So the measure of angle t is roughly 33.6 degrees. Okay, and last but not least here, let's use tangent to help us do this as well. You notice we have the angle theta being shown, which again is a very common variable for angles. And you have the leg that is opposite of that angle. And you have the leg that is adjacent to that angle. And because we have the adjacent leg and the opposite leg, we use tangent. So we write that tangent of theta equals opposite side 8 divided by adjacent side 5. And once again, we simply cancel this using the inverse of tangent. So we write the inverse of tangent of theta equals, and again, what happens is the inverse cancels the function, and you just get theta, which is what we wanted. And if we're going to use that inverse on the left side, we must also use that inverse on the right side. So we have arc tangent over here of 8 over 5. And that's the exact answer of theta. Theta is exactly equal to the arctangent of 8/5. But again, that doesn't mean much to us. And so we go get that decimal approximation. Arctangent of 8/5. So arctangent of 8 over 5 we see is 57.99, which would make us, that 57.9 needs to round up, which is going to take us straight to 58.0. So theta here is approximately 58 degrees, 58.0 degrees. Okay, and that's all there is to it. So use these notes to help you. Same setup to what same idea to whether you're going to use sine, cosine, and tangent, but we can use those three functions to either find missing sides or missing angles.